On October 17, 2014, a team of planetary scientists at the Jet Propulsion Laboratory noticed something wrong with Mimas, a frozen, crater-scarred moon orbiting Saturn. The moon was wobbling. Not a wobble. The surface displacement was measured at 6 kilometers. The predicted displacement for a solid, rigid body like Mimas, a dead moon that had been frozen for 4 billion years, was 3 kilometers. The data had been sitting in Cassini's archives for 13 years. No one had looked closely enough. Mimas should not wobble like this. The physics do not allow it. A solid ice shell, locked in tidal resonance with Saturn, cannot oscillate with twice the amplitude of theoretical models, unless something inside the moon is moving. The scientists ran the calculations again. They checked the calibration logs. They cross-referenced gravitational data from 37 Cassini flybys between 2005 and 2012. The anomaly remained. 6 kilometers of displacement, confirmed and documented across multiple instruments. This was not a glitch. This was not noise in the data. JPL classified the finding as requiring further investigation and restricted the raw telemetry from public release for 8 months. When the paper finally appeared in Science, buried on page 1046 of the March 2015 issue, it used careful language. The abstract said Mimas exhibited librational amplitude inconsistent with a homogeneous interior. That is not how scientists write when they mean frozen solid. By minute 22, you will see the internal model they did not publish, and the reason this discovery changes where NASA will search for life in the next decade. The moon that wobbled wrong. The official story is simple. It's so simple that for 40 years, no one questioned it. Mimas is a small moon, just 396 kilometers across. Its density is 1.15 grams per cubic centimeter. That's barely more than water ice. It sits far enough from Saturn that tidal heating, the gravitational squeeze that keeps Europa and Enceladus warm, shouldn't reach it. The math doesn't allow it. The distance is too great, the body is too small. Tidal forces drop off with distance cubed, not squared, cubed. By the time you reach Mimas, the energy available to flex and warm the interior is negligible. Its surface told the same story: ancient, cratered, geologically dead. In 1980, Voyager 1 passed by and photographed the moon's most famous feature, the Herschel crater, a 139-kilometer-wide impact basin that dominates one hemisphere. The image went viral before the internet existed, not because the moon was interesting, but because it looked like the Death Star. A pop culture coincidence, a meme before memes had names. NASA mentioned it in press releases because it got attention, but scientifically, Herschel wasn't remarkable. It was just proof that Mimas had been hit hard, survived, and then nothing. No fractures radiating outward, no signs the impact triggered anything beneath the surface. No one looked closer, because there was no reason to. Compare it to Enceladus, Saturn's 6th largest moon, only slightly bigger than Mimas but geologically alive, venting water plumes into space, fractures crisscrossing its southern hemisphere, a subsurface ocean confirmed in 2014. Enceladus became one of the most studied objects in the solar system. Mimas became a footnote. The consensus was filed. Mimas, inert ice ball. Surface age, billions of years. Internal activity, none. Astrobiological interest, 0. It was stamped, cataloged, and placed in a drawer. Then in 2014, a team analyzing data from Cassini's close flybys noticed something in the orbital mechanics. Mimas wobbled, slightly, but measurably, more than it should if it were a solid frozen body. The wobble amplitude didn't match the models, not by much, just enough to require an explanation. 3 possibilities were proposed. 1. Mimas had an elongated rocky core that wasn't centered, creating an imbalance. 2. The interior was still warm from an ancient heating event, and the ice hadn't fully solidified yet. 3. There was liquid water beneath the ice. The first two were plausible. The third was not supposed to be possible. The team published the findings. The paper acknowledged the anomaly, but leaned toward the elongated core explanation. It was the safest. It required no rethinking of tidal heating models. It didn't violate any principles. And because Mimas showed no surface cracks, no geysers, no heat signatures, nothing that screamed ocean, the liquid water hypothesis was treated as unlikely. Unlikely, not impossible. But no one expected Cassini's final data drop to eliminate unlikely and leave only impossible. The silence broke in 2014. A team led by Radwan Tajuddin at Cornell University published a paper that should have solved the Mimas wobble. Instead, it opened two doors, both of them impossible. Tajuddin had done the math. He'd analyzed every Cassini image of Mimas that captured the moon's rotation, tracking surface features frame by frame. The measurement was verified. 6 kilometers, double what tidal forces alone could produce. But the data demanded an explanation, so Tajuddin's team presented two. Hypothesis A, an elongated rocky core, a potato-shaped mass of stone buried beneath all that ice, dense, asymmetric, offset from the center of gravity. A core like that could generate the wobble. The physics worked, but the formation didn't. A core that deformed would have required violent tidal heating early in Mimas's history. Heat so extreme it should have fractured the moon from the inside out. Mimas is small, only 400 kilometers across. A body that size, subjected to that kind of internal stress, doesn't survive intact. It shatters. Mimas didn't shatter. Hypothesis B, a global subsurface ocean. A liquid layer between the icy shell and the rocky core would decouple them. The shell could wobble independently, freely, while the core remained stable. The math supported it. The wobble magnitude fit perfectly, but the surface didn't. If Mimas harbored a subsurface ocean, the Herschel crater should have told the story. The crater is 10 kilometers deep. It dominates the moon's northern hemisphere, a scar so massive it nearly destroyed Mimas when it formed. That impact would have sent shockwaves through the entire body. If liquid existed beneath the surface, the crater floor should have relaxed over millions of years. The ice should have flowed. Fractures should have appeared as the shell adjusted to the pressure differential below. None of that happened. Herschel crater remains rigid, sharp, frozen in the geometry of impact. And there's more. Enceladus, Mimas's neighbor, another moon of Saturn, has a confirmed subsurface ocean. The evidence is undeniable. Geysers erupting from the South Pole, tiger-stripe fractures cutting across the surface, heat signatures detected by Cassini's infrared instruments. Enceladus advertises its ocean. Mimas is silent. No geysers, no cracks, no heat. The surface is geologically dead, cratered, cold, ancient. Every feature suggests a frozen, solid body that has remained unchanged for billions of years. Tajuddin stated it plainly in the paper. Mimas liberates roughly 6 kilometers instead of 3. The data was certain, both explanations impossible. An elongated core that should have destroyed the moon. An ocean that left no evidence of its existence. The alibi was false. The suspect was 1,000 miles away. And yet the wobble remained. The scientific community had been handed a paradox. Data that pointed to an ocean on a moon that couldn't possibly have one. Or a core so deformed it defied the survival of the body itself. Two answers, neither one true. The question wasn't new, it was the data that changed. For years, planetary scientists had argued in polite circles in tense conference sessions. The wobble in Mimas's orbit, first detected in Cassini's anamorphic observations, suggested something irregular inside. But irregular how? A deformed core, a frozen asymmetry locked in place billions of years ago, an ocean beneath 24 kilometers of ice. All three explanations could produce orbital perturbations. None could be ruled out with the data available at the time, so the argument stayed open, the models stayed inconclusive, and Mimas stayed a footnote. Then a team at the Observatoire de Paris (PSL) decided to stop guessing. Led by Valérie Laney, they returned to the Cassini archive, not the subset used in earlier studies, but the entire dataset. Every orbital measurement, every gravitational tug recorded from 2004 to 2017. 13 years of spacecraft telemetry, now stripped of noise and fed into hyper-precise dynamical models. The kind that track how a moon's orbit drifts by fractions of a degree over decades. The kind that reveal what's inside by watching how the outside moves. If Mimas had an elongated core, dense material stretched along one axis, its orbit would precess in a specific pattern, predictable, quantifiable. If it had a global ocean beneath the ice, the tidal forces from Saturn would flex the shell. The liquid layer would dampen those flexes differently than solid rock. The orbit would precess in a different pattern, also predictable, also quantifiable. But the models required years of analysis to resolve which signature was real. The paper was published in Nature on February 7, 2024. The result was not ambiguous. The orbital data did not fit the elongated core model. It did not fit the solid body model. It fit, perfectly, the model of a moon with a liquid global ocean. Not a buried sea, not a localized reservoir, a global layer of liquid water 20 to 30 kilometers beneath the surface ice. The same Mimas that had shown no cracks, no geysers, no surface features suggesting anything but frozen stillness for 4 billion years. The moon that looked geologically dead from orbit. That moon, right now, has an ocean. But the data revealed something else, something that explained the paradox. The ocean is young, not ancient, not primordial. Young, geologically speaking. The models constrained its age to between 2 and 25 million years. On a moon that formed 4.5 billion years ago, that ocean appeared in the last 0.5% of its existence. Recent enough that the ice shell hasn't had time to fracture. Recent enough that the surface still looks frozen, still looks dead, because it hasn't caught up to what's happening below. Which means Mimas wasn't always like this. For billions of years it was solid. Then, within the time frame that separates us from the earliest hominids, something changed. Tidal heating from orbital resonance with other moons began pumping energy into its interior. The ice melted from within. An ocean formed beneath a surface that had no reason to crack yet, because the process is still young. The blurry photograph had come into focus, and the detail it revealed was not what anyone expected. A moon caught in the act of waking up. I, like almost everyone, knew Mimas as the Death Star moon, a pop culture reference, a piece of space scenery. I saw the images, that massive crater, Herschel, dominating one hemisphere like a targeting dish, and I assumed the story ended there. A dead rock that survived one hell of an impact. That's what bothered me when I first read Laney's 2024 paper. The data proving this ocean existed was sitting in an archive for 7 years. 7 years. Not classified, not redacted, just ignored. NASA built an entire mission around Saturn's moons. $4 billion, 13 years in orbit. And the team missed this because they were looking where the light was brightest. The term for what Mimas possesses is now formalized in the literature. A stealth ocean. Stealth. Not because anyone tried to hide it, because nature did. No plumes shooting through surface cracks. No tectonic fractures spiderwebbing across ice fields. No thermal hotspots glowing in infrared. Every visual signature that screamed ocean world at Enceladus is absent here. Mimas looks exactly like what a geologically dead moon should look like. and for decades that surface appearance determined where NASA pointed its highest resolution instruments. Cassini's mission design reflected this bias. The spacecraft carried a magnetometer, a plasma spectrometer, radar, tools optimized for Titan's dense atmosphere and Enceladus's active geysers. When engineers allocated observation time, Mimas received 18 close flybys. Enceladus received 23. The difference sounds minor until the data is examined. Enceladus flybys were timed to sample plume composition, map thermal vents, measure tidal flexing at multiple orbital phases. Mimas flybys were reconnaissance passes, gravity measurements, surface imaging, crater counts. The mission treated Mimas as a calibration target, not a scientific priority. The institutional suppression here was not malice. It was neglect born from reasonable assumptions. If a moon shows no surface activity, why dedicate limited instrument time to it when another moon is literally spraying its ocean into space? But the same logic was applied to Dione, to Tethys, to Iapetus. Every quiet moon in the Saturn system received the same treatment. Minimal observation time, minimal modeling effort, minimal scientific priority. A pattern of institutional blindness repeated across 13 years and $4 billion of hardware. The archive told a different story. Cassini's final dataset was released to the public in 2017. Anyone could download it. Laney's team did not access secret files or leak classified telemetry. They used publicly available astrometry, the precise positional measurements of Mimas tracked across thousands of images. The complexity was not in obtaining the data, it was in analyzing it. Building the orbital models required to detect a 1.2-second eccentricity anomaly took years of computational work. The answer was waiting. It just required someone to ask a question no one thought needed asking. Even now, post-discovery, the institutional focus has not shifted. NASA's next-generation ocean world missions, Europa Clipper, Dragonfly, target the obvious candidates. Mimas is not on the list. No proposed return mission. No dedicated orbiter. The assumption that guided Cassini still guides mission planning. If it doesn't look active, it probably isn't worth the cost. That assumption just missed a 25-kilometer deep ocean younger than the dinosaurs. The streetlight metaphor is overused, but it fits. Cassini searched where the illumination was best, where plumes and cracks and heat made the presence of water undeniable. Mimas sat in the shadows, and the team walked past it for 13 years, keys in hand, never bothering to check. The safest thing to do when confronted with impossible data is to doubt the tools that produced it. Call the models incomplete. Say the calculations rest on assumptions that don't hold. Suggest that Mimas is, in fact, frozen solid, and that every instrument, every orbital measurement, every wobble and precession value is just noise masquerading as signal. For a while, that position held ground, but by 2024, it collapsed. Valerie Laney didn't use libration data. He analyzed something entirely separate: Mimas's orbital precession, the slow drift in how its ellipse rotates over time. Different method, different data set, different mathematical framework, same conclusion. The moon's interior is not rigid. That's no longer interpretation, that's confirmation. When two independent lines of evidence, libration measurements from Cassini images and orbital precession from decades of positional tracking, both point to a deformable interior, the result is not a mistake. It is convergence. The detective has crossed off another suspect. The doubt the model's defense is gone. So the argument shifts. If Mimas truly harbors a subsurface ocean, where are the cracks? Europa's surface is a shattered mosaic of ice fractures. Enceladus vents water into space through tiger-striped fissures at its south pole. Both moons display the visible scars of liquid water pushing against their ice shells. Mimas displays none of that. Its surface is ancient, cratered, intact. That sounds like damning evidence until you ask a different question. Not why aren't there cracks, but when would cracks form? The answer comes from the timeline itself. The ocean beneath Mimas formed somewhere between 2 and 25 million years ago. Geologically, that's yesterday. The ice shell above it measures 20 to 30 kilometers thick. Water pushing upward from that depth doesn't fracture the surface overnight. It takes time, pressure, thermal cycling across millions of years. Mimas hasn't had those millions of years yet. The lack of surface cracks is not evidence against an ocean. It's evidence of youth. The ocean is too new to have broken through. Then there's Herschel, the massive impact crater that dominates Mimas's leading hemisphere, 1/3 the moon's diameter. The kind of collision that should have shattered a body with liquid inside. Europa's Tyre crater is smaller and shows clear signs of viscous rebound, the ice shell flexing over a subsurface ocean. Herschel shows no such deformation. Again, that looks like proof of solidity, until you align the timeline. Herschel crater is ancient. It formed billions of years ago when Mimas was frozen all the way through. The impact struck a solid target. No ocean existed to absorb or redistribute the energy. The crater froze into the surface exactly as it formed and stayed that way for eons. Then, within the last 25 million years, something changed. Tidal heating intensified. Ice began to melt from the inside. The ocean emerged beneath a landscape already set in stone. Herschel doesn't disprove the ocean, it predates it. Not a misinterpretation of models. 2 independent data sets confirm it. Not a lack of surface fractures. The ocean is too young. Not an intact impact crater. The crater is too old. The detective has eliminated every suspect. What remains is not comfortable. It doesn't fit intuition, but it fits the data. Mimas is not a solid body. For decades, planetary science looked for life in the places that looked alive. Cracks in the ice, plumes venting vapor, smooth plains that scream, something is resurfacing this world from below. Enceladus fit the profile. Europa fit the profile. Titan, strange, hazy, methane-soaked, fit the profile. Mimas did not. Its surface is older than most of Saturn's moons. Its craters run deep. The Herschel impact alone should have shattered it to rubble. And yet the moon held together, silent, unremarkable. For 43 years, no one thought to look closer. Not because the data wasn't there, because the surface told a story everyone believed. And that belief just collapsed. You, right now, are looking at a solar system that just got much bigger. Mimas proves that an ocean, the primary ingredient for life as we know it, can exist where there is no surface evidence for it. No plumes, no cracks, no smooth terrain. Just old ice scarred by impacts, hiding a young sea beneath. The discovery forces a single, uncomfortable question. If Mimas fooled the entire field for 43 years, what else is being misread right now? I do not know what is in that ocean, but the discovery forces a reevaluation of dozens of other so-called dead moons. Dione shows subtle libration hints in its rotation, wobbles that suggest internal motion. Tethys has thermal models that support a buried ocean if the right salts are present. Voyager captured strange, grooved terrain on Uranus's moons Ariel and Miranda, features that, at the time, were dismissed as ancient geology. Were they? The Mimas discovery transforms these small, icy worlds from geological footnotes into a whole new category of astrobiological targets. NASA's proposed Uranus Orbiter and Probe mission, scheduled for the 2030s, will carry ice-penetrating radar. The European Space Agency's JUICE mission will pass Ganymede, Callisto, Europa, each one now under review for ocean detection beyond surface geology. And yet Mimas itself is not on any return mission list. Not Europa Clipper, not Dragonfly, not the Uranus probe. The agency that just discovered an ocean on Mimas has scheduled zero follow-up. Why? Cassini is gone, but its final gift was a blueprint. Look deeper than the face of a world. Because Mimas was hiding in plain sight, not in a distant star system, not in a nebula 40 light-years away, 390 million kilometers from where you are sitting right now, a moon the size of Arizona, with an ocean younger than the Appalachian Mountains, orbiting a planet humans have known about since Galileo first pointed a telescope at the sky. The discovery is not just about Mimas. It is about every object in this solar system, and beyond, that scientists looked at once and decided was dead. Every moon, every distant Kuiper Belt object, every frozen dwarf planet at the edge of the heliosphere. How many of them are still being misjudged? Right now, somewhere in the outer solar system, there may be another ocean, warming, stirring, writing its first chapter in liquid chemistry, while observers from the surface see only ice and assume nothing more. The question is not whether life exists out there. The question is whether anyone is looking in the right way. If you have access to the Cassini archive, specifically the astrometric data sets from 2004 through 2017, the files are public. The libration analysis that cracked Mimas open is sitting there, waiting for someone to apply it to Dione, to Tethys, to a dozen other worlds already photographed. The data is not hidden, it is unread. Tell me what you find.